Since this reaction is an overlapping of p orbitals, there is no opportunity for anything else to take place besides a syn addition, which means that both of the bonds are going to be formed on the same side, either both on the bottom or both on the top. Since the p orbitals are in the same plane, and these will be in the same plane as each other, they have to line up in order for the reaction to take place, so it cannot have one on the top and one on the bottom, or vice versa. So this is a simple rule to understand and to see visually. If someone has models, you can just make them and try to line them up and you'll see exactly what I'm talking about. And the other rule to think about is the Endo rule. And what the Endo rule is when there is an electron withdrawing group like this one, although I made the example down here, the electron withdrawing group has a tendency to occupy a certain position when there is an addition. So here are the different positions. There's an endo, which is closer to this double bond over here, and there's an exo position, which is pointing out. The electron withdrawing group tends to occupy the endo position. And if we look at what's going on in the reaction, say we've got this ring right here, here are two double bonds. The reason that the electron withdrawing group tends to be in the endo position is because in this transition stage, which is a little bit hard to see the way I drew it, but again, if you have models, it's a lot easier to see what's going on. When it occupies the endo position, it's closer to this double bond over here, which will be formed in the new transition state. So in the transition state, these new sigma bonds are forming, and this double bond over here is forming. Since this has a lot of electron density, what this can do is form a slight overlap between the double bonds and the electron withdrawing group, whatever that may be. It will lend some partial electron density to this, so it helps stabilize the transition state, is all it does. But if it's in the exo position, it's too far away in order for this to happen. This is why it tends to be occupying the endo position, because it helps lower the energy required to transition into the new state. So looking at this planarly, maybe it might be more helpful than to see this attempted three-dimensional drawing. Knowing that this electron withdrawing group here can add electron density, or to help lend electron density to a bond that's going to form over here. Looking at it aerially, which way is this likely to be adding in? This way or this way? This way most likely, because it's closer to this new double bond forming. Over here we can see this aerially a lot easier probably than this. So it's really just the way that this is going to be added, the stereochemistry. It's going to occupy this endo position. It's going to be closer. If it were flipped the other way, it would occupy the exo position, pointing out. So if you imagine it three-dimensionally now, if it being added below here, the hydrogen would be over here somewhere, and then this would be pointing out over there. Whereas this one over here, the electron withdrawing group would be closer. It'd be something like this. Again, with 3D models, this is a lot easier to see. I don't have a camera, otherwise I would just use them myself, but maybe I'll go to a store and just buy a cheap camera, because it really is super clear and easy to see when you've got a set of models in your hands.